The assignment that's due tomorrow is due tomorrow at 11 p.m. Okay, so just share it to me. Share it to me by 11 p.m. or stop working on it by 11 p.m. All right, and it'll be 11 p.m. for the rest of the assignments too. And assuming that the sharing works well, which I think it will, all the rest will be submitted in that same way. Any questions about the assignment? More meta questions. If you have specific questions, office hours is the best time here on the piazza. But general questions like that. So, by the way, it didn't say 11 p.m. 10 minutes ago. The question came up, and so I put it on there. Okay, so we were talking about regularization techniques. And in particular, you guys had just gone through and come up with a number of different ways to do data augmentation. Right? So we were on this one. And the data augmentation, Ali, why is that of use? What's the good part about data augmentation?
Just gives you more variation of what you could see of what types of people you use.
Gives you more variation, right? It's like you had a larger training set, right? Except you didn't have to pay for the labels, because labeling is expensive, right? Imagine if you have to go through a bunch of pictures and figure out, is this a cat? Yes or no, yes or no, yes or no. You could do that, I suppose, all by yourself, which makes sense because you're not making a lot of money right now. You could, so grad students typically might do that. How else might you do labeling? Anyone?
Pay someone to do it.
Pay someone like who?
I think there's a term like Turks.
Turks. Mechanical Turks. So this is Amazon runs this program called the Mechanical Turk program. And the idea is you pay humans to do human-like little tasks. So you might pay half a penny a piece for them to label and say whether it's a cat or not. Right? Now, someone's going to be zipping through for half a penny a piece pretty quickly, right? So they might not be right. So maybe you'll pay 3 groups of people to do it, right? And then do best of 3 to determine the correctness. But it's going to cost some money. There are in some ways very sneaky ways to do labeling. Google used to offer a service called Google 411. So you could, I don't even remember the days, but you could call 411 back in an old phone, and you could find out, what's the number for Joe's Pizza? Okay, and they would tell you what the number for Joe's Pizza is, right? And Google 411 would do this, but it'll do that for anyone in the country for free. And it would also say, would you like me to connect you? So it was a free call too. So it was pretty handy. But what it was doing, the advantage to Google was that they were getting labeling of their speech recognition. So when you said, I'd like the number for Joe's Pizza, please, Joe's Pizza in Manhattan, it would respond back and say, did you mean the Joe's Pizza on 3rd Street in Manhattan? Or did you mean the something totally different? And you'd say, I meant the first one. What you were doing just there was labeling for Google, right? Now, it was a valuable service they were providing, but it was, they didn't do it for nothing. So labeling can be expensive. The data augmentation basically gives us a way to extend our data set, our labeled data set, without having to pay for more labeling. So that's one regularization technique. Regularization techniques in general, Santi, what are they good for? Why do we have regularization? Why are we doing it?
So we can get better learning of set data.
Better learning, in particular. How do we measure better learning?
A lower loss function.
Lower loss function on what data set?
The validation.
The validation data set, yeah. The regularization enhances generalization. Okay, so that's what regularization is for, is we do regularization for better generalization. Sometimes at the loss of our actual accuracy. So we may have a higher loss on the training data set, but we're willing to pay for it by getting better generalization and having a lower loss on the validations. Does that make sense? Okay, so it's just another way of reducing the amount that the model can vary, reducing how much the parameters can change. So by throwing more training data at it is one way that says, sorry, you can't just have your parameters however you want. They have to try and fit this large set of data, so therefore you have a kind of small box in which it can work to get a small loss. So we're going to look at a couple of others. When you're doing data augmentation, where in this picture, what's changing when we're doing data augmentation? That is, what are we playing with here? Where our choices are the loss, the optimizer, the thetas, f, y, x. Brandon.
Is it the optimizer?
Okay, so optimizer is basically right now the part that says, I think it's almost, no, it's a couple lines, right? We do a gradient descent, and then we say theta minus equals lambda times the gradient descent, right? Roughly, that's what it is. So where in here are we dealing with new data? Or are we doing new data in here? Or not? So where might we be?
The x and the y's.
The x's. And the y's we're duplicating, right? We're not really changing. But basically this is here, data augmentation. Okay? And we're going to look and see we can actually change it almost any place in this diagram to do regularization. But that's the first part, is the x's. The next one we're going to look at is the one we skipped on Monday, which is adjust the loss function. Daniel, where on this diagram do you think adjust the loss function, what gets changed?
The loss function.
Well said. So adjust the loss function here is a form of regularization. And let's look at it. So the idea is we've got some loss function, let's say for a batch of data. Okay, it might be a full batch, might be a mini batch. We're just looking at our loss. And I'm putting the subscript b just to distinguish it from a single instance, single training instance. So it's a group of instances. So we have some function here, whatever it is. In our case, we've been using, I know it starts with an, is it Nolan? Okay, all right, Nolan. Sorry, but I guess my question is, what have we been using for our loss function?
Sum squared.
Sum squared, yeah, average sum squared. But we could use whatever we want. The loss itself doesn't say anything about the complexity of our parameters. Right, so if we're using a 10-degree polynomial, it could do whatever it needs to do those parameters to decrease that loss for a given batch. What if we could find a new loss, L prime? Okay, so L prime of a batch equals L of our batch, however that's defined. And then we're going to add some penalty based on our parameters. So it's just a general description here. Some penalty, and we're going to have some alpha parameter just so we can adjust, because we probably want this to be in the same kind of range as here. Alpha is, in fact, yet another. So this is YAP. YAP stands for? Jack? Help them out, anyone? Call a friend?
Yet another hyperparameter.
Yet another hyperparameter. Okay? Because we have a lot of them. And our penalty, we haven't described exactly what this is, but it's going to be some penalty based on our parameters. If they're too complex, we're going to charge that to the loss function. So when we're doing our gradient descent, it's going to have to look and say, well, for a particular parameter theta, do I want to decrease the loss by decreasing the original loss? Or do I want to decrease the loss by having a lower penalty? Or some combination of those. But it can't just arbitrarily change thetas to decrease the original loss. without potentially increasing the penalty and making it not worth it. Concept makes sense? So let's look at our polynomial case again. So we have a 10-degree polynomial. That's too many. I don't want to write that many. We're going to have a 3-degree polynomial, right? So f of x equals a0. I can write it this way. We have a d-degree polynomial. So we have a, I, x, x to the I, right? For some number of I equals 1 to d, 0 to d. Okay, so a0 plus a1x plus a2x2 plus a3x3 and so on. We know what our loss is. That equals the sum over all of the x's and y's in our batch of yes? Okay. Now let's come up with what might be a good penalty. So penalty of our thetas, where our thetas is just another name for Ezra, in our case.
Theta is another name for the optimizer function.
The theta is not the optimizer function. The theta is what the optimizer optimizes.
Like, yeah, the optimized function.
Okay, so it's not quite. Yeah, so what are the parameters of our function here?
The parameters are fx.
That's our function.
Oh yeah, parameters are a and x.
Just a, right? And then there are two different problems here, right? If I just look at f of x and ask what's the parameter of f of x, it's x. But in our case, as we talk about our machine learning parameters are our a's, a sub i's, because that's what we're learning, right? What we're learning is our a sub i's. So this is really our penalty of our a's. Okay. Any ideas for a penalty, Matt? In the front, Matt. Pack?
Yeah. Penalty.
Yeah, so I want to say, I don't want my a sub i's to get too outrageous.
I guess you can make you can limit how big it is and then just multiply by a small factor.
Let's give me an example. So limit how big they are by
Well, how are we? Okay, so.
let me give you a hint, because of course I know where I want you to go. So here we are trying to limit how bad the prediction is from the actual, right? And we're doing that by charging, in some sense, charging the squared error. Here, if we want to charge a penalty on A's for getting, let's say, too big, how can we do that? So let's say I do a sum over all i's. I'm going to do a penalty. Give me a penalty for one weight, a sub 3. Oh.
A sub 3 squared.
Sounds good to me. So we'll just say we'll take the square of the coefficient and sum those all up. And if that gets really big, we'll call that a complicated model. And if that gets really small, we'll call it a simple model. It kind of makes sense, right? If you had all of them 0, that's clearly very simple, and there's no penalty. And if they're all 100, that seems pretty big, and that would be a large penalty. So we could do something like that, a sub I squared. Okay. This is called the L2 norm. All right. I'll mention another one in just a second. So you remember the case where we had 10 instances, 10 training instances, and a 10-degree polynomial, and how we decided it fitted exactly? Well, if we choose our hyperparameter here correctly, and we add in and use this penalty, there's going to be a discouragement to be using some of those coefficients, or at least using them very much. So there'd be a trade-off between exactly fitting and making our a sub i's be large. And so it might choose, if your data that's incoming is best fit by a quadratic, it might mostly choose a quadratic and have very little higher order coefficients. On the other hand, if it was best fit by a straight line, the a sub 2 would probably be very small also, because there's no free lunch for it. It can't just choose to try and fit everything without facing this penalty. Does that make sense?
Would you want to like have a higher penalty for like higher order A's, like A's that attack or that multiply by the x to the 10, 1?
That seems reasonable actually, to say if you've got a large x to the 10th value and small others, that's more complicated than a large x squared a2 and small all the others. So you could certainly do something where the larger I is, the larger the penalty is. I don't know what you want to do, maybe something on the order, you could do I a squared maybe here. I have never thought of that, but that would certainly be reasonable. Another option you could do is you could instead, so this is another possibility, just use a sub I. Except that by itself has a little bit of a problem. Nick, what's the problem?
They're positive and negative.
Positive and negative. So how could we fix that?
Squaring, I thought.
Squaring was one part, but I don't like this penalty kind of, so how could we fix positive and negatives?
Absolute value.
Sounds good to me. Absolute value. So this would be an L1 norm. For some reason, using this L2 norm is also called weight decay. For some reason is not this week's homework, but next week's homework. So you're going to actually go through and see why that is. But basically, using this L2 norm on the loss is equivalent to changing the optimization function so that the optimization function looks like theta I equals theta I. Let's see, so we're normally theta I equals theta I minus lambda times the gradient descent, right? Or times the gradient. Instead, we add a factor here on the theta I, so that theta I becomes smaller each term. So we have a value here, 1 minus alpha lambda times theta I. Okay, the value of this doesn't particularly matter. What it is a number between 0 and 1, such that we have this exponential decay of theta I. So every time we update theta I, before we update it, before we apply this either increment or decrement based on the gradient, we reduce the value of theta I. So that if we had a large parameter that became 50, it would tend to be getting smaller and smaller and smaller over time, all on its own, as we did our gradient descent. This is mathematically the same as this, and that's what you're going to show in your homework. Does the concept make sense, though? So, yeah.
I'm still wondering why you have a gamma and lambda term. Maybe that's something that you're doing.
It's actually this lambda. Where'd the gamma go over here? It's the gamma for the penalty.
Okay.
So remember we said that the loss prime equals the loss plus
Oh, okay.
gamma
Sorry.
times the penalty.
Yeah, that makes sense.
Okay, so this gamma is this gamma. So the fact that you can, in a way that you guys are going to show and I'm not showing right now, can move this modification from the loss function to the optimizer. So this is weight decay. Normalization. Either here or here. Okay? In the general case, it's in the loss function. For this particular choice of the L2 norm, it happens to be the L2 norm you can either do here or you can move it into the optimizer because it just kind of flows through into here. Questions on the adjusting the loss function?
So just to clarify, it's only the L2 norm?
It's only the L2 norm that actually moves from the loss function over here. If we use the L1 norm, we'd have to be applying it here at the loss function. But it's very common to use that L2 norm and to use this weight decay and just to do it in the optimizer. All right, we're going to look now at injecting noise. So I'm going to provide you, let's say we have let's not do cats, let's just do face recognizers. Okay, so we've got a face recognizer, and here we've got a face. Okay? And so this is part of a labeled data set. This is, yes, a face. All right? We've looked at the data augmentation we can do. Now we're going to look at, you might consider it still another form of data augmentation, although it's a little weirder. So we are going to add into here some noise, which I'm going to represent right now as just kind of an epsilon. Okay? A little bit of noise for every pixel. And that's going to, and this is conceptually, right? This is not actually, but conceptually, we've got now a face that is a little modified, right? Really, it's only conceptual because we're really just touching every pixel here, and the pixels don't make the lines wavy. But it's the idea I'm trying to provide you. So the theory here is, if you've got, let's say, a picture, and you tweak some pixels by minute amounts, that shouldn't really change whether it is a face or not. Okay? And so in some sense, this is a form of data augmentation. The noise forces the model to be more robust in learning. And also probably will generalize better because depending, of course, on the domain, but in the wild, likely your inputs will have some fluctuation in them. There'll be some noise in the inputs. So we'll be learning this better. Yeah.
So is this the same as data augmentation, just adding noise in the data augmentation?
It's the same as that, yes. Yes. So that will force the model to be more robust.
So like the housing example, would it be like you add like a couple square feet or something? And
Yeah, that's a good example. So our particular input training example might be 2,400 square feet and 3 bedrooms. And we might say it's 2,410 square feet. The 3 bedrooms are a little harder to change. We probably have an integer there. And so maybe, 1 in 1,000 times, we actually change the 3 to a 4 or the 3 to a 2.
Do we have to do the same amount of data augmentation on every single element we have to avoid like?
We don't want, if you weren't careful, yeah, you would be biasing. And so you have to either, you do really want to be doing the same amount of augmentation. Not the same exact augmentation, but the same amount of augmentation. So you might be randomly choosing, in the original case of data augmentation, whether to flip or to rotate or to zoom or to scale. But every input should have the same chance of having the same thing happen to it. Does it make sense? So this is one place we can also do noise injection. I am going to hold off until probably Monday to discuss how you can do noise injection into the Y as well. Okay, but that's possible. Which seems weird, like why would you want to be changing the ground truth? But it can be useful. Where else can we do noise injection? We can actually do noise injection into here. So noise injection into the thetas. Actually go through and as you are calculating F, okay, so as you calculate loss, which as part of it means calculating F, perturb the thetas. Okay, just make small. How small? That's a yet. Okay? Yet another hyperparameter is what you're using as far as that noise injection. But perturb this slightly. And let me give you a conceptual why this might be useful. But does what we're doing make sense? So basically, as you calculate F, you make this slight perturbation. And what that means then is the y hat you get out is slightly different from the y hat you would originally get out. So it really, we're adjusting noise in here, which is causing y hat to be modified. So the idea is, let's say this is a loss function. So our loss function might look like that. I don't know, and that, let's say, something like that. So this is our loss, and this is kind of our theta as it changes. And here's my question. Rory, would we rather have a model that's trained such that we're in here or in here? The losses are the same.
In the wider?
Why in the wider?
Because we have a wider range that of a low loss.
Yeah, we have a wider range. We're more resilient to change here. This one seems very sort of specific. If we found a very tight little area exactly where these thetas will work, and it seems less likely to generalize than if we have a more wide area. So the noise causes us to find a loss in here rather than in here. Because when we're looking at our theta might be here, and it might be here, and it might be here, and it might be here, depending on the noise we added at any particular time. Does that make sense? Questions?
So the noise has to be big enough to get you out of one of those dips?
The noise has to be big enough, yeah, to such, exactly. Because what will happen is, let's say your theta is right here, but you add noise on a particular batch, and your noise takes you, let's say, up to here. And then your gradient of descent would take you out of it. So yeah, your noise would exactly have to be big enough to get you out of a narrow, plateau is not really the right word for this, but valley. All right, second. All right, that's enough for the noise right now. Let's go into the multitask learning. So just remember that the one more place we can inject the noise is in the Y's, and we're going to do that on Monday when we get into classification, because it'll make more sense then. Multitask learning. So here's the idea. Let's say we have two tasks we want to do. We've got, is it a face? Okay, that is just a categorization question. Okay, face or not face? And that can be yes, or it can be no. And let's say we've got another problem, which is, where's the face? And so we give in a, supposed to be the same face. It's roughly the same face. And the job is to say the face is here, right? Just like all your cameras do. I'm going to change this problem slightly. Okay, I'm going to assume we have faces for a moment. And I'm going to say not, is it a face? Is it a happy face? Yes or no? Okay, so you can imagine creating a model for this, creating a model for this, training them. We can use the same training X's. We'd have to have different Y's though, right? We'd have to have, in this case, Y's with bounding boxes, and in this case, Y's with yeses or nos. Ones and zeros. So this problem would have some parameters, theta sub happy. Right? And this problem would have some parameters which are theta sub, I'm going to call it loc for location. And let's say we don't have a huge number of faces. How do we know we don't have a huge number of faces? Because when we try and do our training, we're finding that we are what? Rachel, how do we know we don't have enough data? In general, when we're doing learning, how do we know we don't have enough data?
Oh, if you're underfitting.
Okay, so we're underfitting if we don't have enough data, and also if we're underfitting, we know we need a richer model, right? Really, to tell that we don't have enough data means that we are overfitting, and we need more data. So we find so basically this is sort of the cycle we're in. We're underfit. So what do we do when we're underfit? Add complexity. So make the model more complex. And basically, we keep going in, doing this while we're underfit, right? Till eventually, what probably happens? Matt in the back?
It becomes too complex and starts over.
Yeah, then we start getting overfit. And so if we're overfit, our fixes are, Susan, what's one fix we can use to fix overfitting?
We could have a less complex model.
So we could reduce the complexity of the model. What are ways we have to reduce the complexity of the model? We could reduce the degree. Unfortunately, it turns out we just made it big enough so that we're not underfitting. So we would use one of these techniques, right? Regularization. Which basically says, okay, you've got a particular model there. Let's try and have the same number of parameters, but still make it generalizable. So regularization is one way, and what's one way to always reduce overfitting?
More data.
Yeah, more data. More training data. All right. So here's the idea of what we're going to do here. We have, if we look at sort of the number of parameters in the checking to see whether it's happy or not, and the number of parameters in checking the location, the sum of those is going to be less than, probably, a problem where we do both at once. So we say we're not going to train one model to check if it's happy and another model to say where the face is. We're going to train one model to rule them all. Okay? And it's going to take this and it'll say happy and where. Because we can certainly have models that output more than a single value. Very common to have models that return multiple values, in some cases tens of thousands of values. So a good example, how many of you guys have heard of Alphago? So, right, this is the deep mind, deep learning, and reinforcement learning Go player, right? That's very good. In their initial version of that, they had two neural networks. One to predict, given this game state, right, given this Go board, how likely am I to win? And a second neural network that said, given this game state, what's the best place to play? And in the second version, they said, why do we have two different neural networks for this? Let's have one neural network for this. We can make it more complex, add more parameters, and yet still have less than the sum of the parameters we had before, and so train it better. Another way to think of it is, I mean, in a humanistic way, is it's cross-training, right? You're kind of training both, I don't have a good analogy here, shooting on goal and passing to your soccer teammate. And it turns out a lot of that leg movement that you're learning is useful for both. Right? So why waste it learning it on one and then start completely fresh on another? So each of these is going to have to know things like probably, you know, some representation of what hair is and that there are eyes and nose and a mouth. Right? It'll need to know eyes and nose here to try and find the mouth, probably. Okay. So cross-training or multitask learning is a very useful regularization technique.
I just want to double check. So when you do both of them, you have more parameters or less parameters?
So if you do each one individually,
Yeah.
you will have in total more parameters than you would if you tried to learn them together. Right? So here's my model. This model, let's say, is this big. And this model is this big. And this model can be larger than both of them, but yet still smaller than the total. Does that make sense?
Yeah, I just thought like that was like the sign was longer.
I like that a lot better. Okay, yes. So two simpler models in total can still have more parameters than one more complex model. Okay. Early stopping is the idea, which we've really already looked at, where when your validation loss starts going back up, don't go that far. Right? So if we look at time, and loss. And this represents our training data. And we would expect the training data. It may asymptote somewhere, right? It probably won't asymptote at 0. It asymptotes somewhere likely, because there's some inherent unpredictability about the incoming data. And our validate, so this is the training. Our validation loss often will kind of be close to the training loss, but then we'll start going up as we, and in this area of the graph is Leo. What's happening here?
It's overfitting.
Yeah, overfit. So the idea is if you're running 100 epochs, every epoch you might graph or print out the validation loss and the training loss. And you would normally see the training loss go down, 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 and the validation loss go down, 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 down before it starts going up, 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 up. So if this is 100 epochs, where do we want to stop? Mo.
Around 70.
70 sounds good. So let's say 70. So here's one way we could do it. We write a for loop. We have our kind of loop, and we have a, guess we call, what's the number of epochs? What's the name for something like that? It's an example of a yap, right? Yet another hyperparameter is the number of epochs. So we run it first with 100. We go look, we see, oh, it turns out it starts increasing at 70. How's the model at the end? Good, bad, bad. Doesn't generalize well at all. So we throw that away. And we go back and run again with 70. That's fine if it takes 45 minutes. But if it takes 2 weeks on 1,000 machines, you're like, I wish I hadn't gone to 100. You had a question there?
Oh, no.
Okay. So what's the solution? The solution is, in your training loop, right, for epoch in range 100, we're not ever going to put a naked constant like this in there, but it'd be some num epochs. We're going to adjust our theta, do mini batches, do all sorts of stuff, and then print training loss. So loss of our training data. Print loss of our validation data. And save theta. Okay? So save theta, to theta dot epoch. That is, when we're done, we're going to have 100 different files. Epoch 1 to epoch 100, and they'll have all of our parameters from each epoch. And then we can just go back and say, oh, let's go get 70 and use that. Or we can actually add code in here that says, I'm going to programmatically figure out as we start actually increasing and just stop. And not do the remaining 30 because there's no reason to. That's also possible. Questions?
Does the graph always kind of look like that, or is there other times where it would go up and then start going down again, or we wouldn't want to just go based on if it starts going up?
Well, yeah, this is the prettiest. So this is a smoothed version of it for sure. So your validation loss can definitely, kind of be very wavy, and that's why programmatically can be a little more difficult, and it's much more easy to see by eye. But yeah, it is not smooth like this. It is jagged.
Since we're Sorry. Since you, I know it's tough for us to have a sense of like what this will look like going into it, and if you have obviously the computing power and the time to be able to like let these things run, is it better just in general to just have that sort of setup of like run it for as long as you feel like we can, and then check later afterwards about what we think it's going to be, just because it's more generalized?
Yeah. So actually, no. If you've got a 2-week running program or longer than 2-week running program, what you actually want is to be seeing this graph live. So you can go and look day by day and see, at some point, this is not working. I can save my last 5 days by just stopping it. We will look at, later in the course, Tensor Board. So this is part of TensorFlow. Well, it's actually, it's packaged with TensorFlow. And it's a mechanism intended specifically for machine learning to be monitoring log files, pulling out information, generating visualizations, so you can see what the heck is going on. So you could be looking at losses, you could be looking at all sorts of other different important information. One reason you wouldn't want to wait your final 2 weeks is, what if your graph just looked like, this? You screwed something up, and like the training is never get any better. You don't want to wait 2 weeks and thousands of machines to find out. Other questions?
Does it
Santi?
present an issue sometimes saving it if it's too large? If the model's too is it a terrible situation?
It depends. So if you're running on a sort of a giant server farm, you probably have some sort of a distributed file system where it's pretty easy to be saving data with. It's hundreds of millions of parameters is probably a good size. I would have to look and see what like AlphaZero was, Alphago, how many parameters that was. But I think it's in the range of hundreds of millions, let's say, but it's not more than that. So, other questions?
As
Lauren.
we're going, could we delete the data that's associated with the high validation training loss?
Sure. I mean, it's just what's another acronym? SMOP. You guys familiar with that? It's a simple matter of programming, right? So yeah, any problem? Oh yeah, I can. So yeah, you could program to do whatever you want. You could be looking at a exponentially smooth average of the validation loss and use that to determine as it starts to increase and both stop saving. You could, as the validation loss is going down, only be saving the last 10 of these. There's all sorts of stuff that you could code up. Other questions? And the other thing is you'll find as we get into this, so when you have training loops and things like this, we're going to be using Keras. And in Keras, there are hooks you can put in. So you can have a hook where you write that gets executed at the end of every epoch. And then you can, for instance, use that for early stopping. You could put in code and say, I'm looking at these various things, and I've decided, let's stop now.
Do you ever run something for just a while to see how your function does with the data? Because it takes 2 weeks. When you want to how would you decide if your function should be changed or not?
So you'll use less data typically to begin with to just get an idea that it's sort of working. And if you want to be, let's say you may be going from let's say recognizing faces. So you may, let's say we have a same number of happy faces as sad faces, okay? And so the first thing you would want as you were doing your training was to verify that you could get something better than 50%, all right? And once you're getting 53%, you're like, okay, I'm happy, I can prove I can do something that's better than random. And from there then, maybe you find that with 150 training examples, not too many, and something you could just run in 15 minutes, you can get up to 75% accuracy. And now then it might be a matter of, okay, 75% accuracy on the validation set. Now let's throw a bunch more training set of let it run longer and see if we can get that 75% up to 85 or 90 or 95. So does that help?
Yep.
All right. So the next one then is ensembling. I'm going to save this for a moment. It won't be on any exam, but SMOP stands for? And so a WAG is. What's a swag? Let's see. Does anyone know what a WAG is? Someone says, how long is this going to take? It's just a wild ass guess. Okay? And I don't know where, somehow I have an S in my mind. I don't know what the S is for swag. Anyway. So the idea of ensembling is sort of using wisdom of the crowds. Right, the theory, so this all kind of goes back to, I think it was Galton that did this, the same guy who came up with the reversion to the mean. He went to a fair, and let's see if I get this right. I believe that they were having a contest where you tried to, the modern version is guess the number of beans in a jar, and I think then it was guess the weight of this steer or pig or something, animal, okay? Guess the weight of the animal. And so people wrote down their guesses and put them in that's where the jar comes in a jar. And then at the end, the one who came the closest won something. Maybe they even won the animal, I'm not sure. So what Galton does is he got actually access to the jar afterwards. And he went through and looked and found that let's see if I get this, the average, and I don't remember whether he used mean or median. I remember he invented the name median. The average was better than anyone's individual guess. And that's kind of the wisdom of the crowds. So people are coming in with all sorts of different information. One person might be coming in and looking at the size of some arm of the calf, leg, the front right leg of the calf, and looks at its diameter and bases an estimate on that. And someone else might be a strong man, comes in and kind of lifts it up and says, oh, that feels like about 1,300 pounds, right? And someone else comes in with all sorts of different information that they're using for this. And so the ensemble is just say, don't ask one person, ask many people and average their answers, and you'll be better off than just one. In the same way, rather than just taking a single model and asking it for its prediction, ask multiple models and combine them together to get an answer. So we take model 1 and model 2 and model 3, let's say. And we have X that's incoming. Now these are all trained models. Okay, so I'm going to assume for now we've trained different models to do the same task. And each of this is going to come out with a y hat, right? So this is y hat, let's say sub 1, y hat sub 2, y hat sub 3, and our overall y hat is going to be a combination of these. One possibility would just be a mean, or a median, or some linear combination of them, right? So maybe we have found out that model 3 is really not that good, right? We only give it like a 4% weighting, and these guys are pretty good. So this is like a 40%, and this is 4%, and this is the remainder percent, 56%. right? So we might say that real y hat is 56% of y1 hat plus 40% y2 hat plus 4% y3 hat. And that's going to be our overall or ensembled prediction. How do we know what these numbers are? We're going to have to try and kind of learn those. Maybe we just take the models, try different numbers, see which one gives us our overall best results on our validations. Questions on this? Okay. This is better than just using a single model in almost all cases. Because really it just reverts to, if you have two crappy models and one good model, maybe it's just going to be 100% of the good model and 0% of the crappy models. Okay. So where do you get these models? Santi. Hyperparameters is a good way to get it. So you might use different hyperparameters for different models. Let's say you do 3 to begin with. So you have maybe you adjust the learning rate, or you're adjusting the gamma of the weight decay, or you're adjusting the sorry, we already did the lambda of learning rate. What else can we adjust? Yeah, check. Number of epochs. Anyone else? What else have we seen in terms of hyperparameters?
Complexity of the
Josh?
function.
Complexity of the function, sure. So that's, in some sense, it's sort of a hyperparameter. When we're actually defining what the model is, I sometimes think of that as adjusting the architecture of the model. Batch size. If we've got noise that we're injecting, what the parameterization of that noise is. All those things we could use. So we train 3 models. Not a problem if the models take half an hour to train. But if the models take 2 weeks and 1,000 machines, then training 3 models is 3 times as costly as 1 model. Another thing about the ensembling, how many of you people here have heard of Kaggle competitions? A few. Kaggle. So Kaggle.com has machine learning competitions. Where basically you get given a data set, you get given a loss function, which you're going to be measured, and you try and train. So you get given training and validation set. Roughly, you get given a bunch of data that you parcel out how you want to. And then when you're done, you operate on some data they've given you that's unlabeled and give them back the labels, and they evaluate that. Where does this data come from? Companies that need machine learning results of things. So often there will be rewards for this. Like there might be a 3-month competition in which you can run, and the winner gets $25,000 or $50,000, something like that. Okay, so not a bad racket to go into. And the other thing is many winners of Kaggle competitions go on into nice machine learning careers. Here's why I'm talking about this, though. So towards the end of the competition, here's what happens. You've got, let's say, three teams. Let's say 2 of you, went in a team together, and some other people went in teams together, and you've all got models, and you're doing good. You're at the top of the leaderboard. Okay. In fact, let's say you 2 are at the top of the leaderboard. Okay. It's not just you 2. It's you 6 are at the top of the leaderboard. So you're all working together. You're sharing your machines. You're working. You've got a great model. You like it. Number 1. Row 2 and row 3. Row 3, I'm sorry, you're in 3rd place. And row 2, you're in 2nd place. Okay? But all of a sudden, then, you turn around and you talk to Nick and say, Nick, what if we ensembled our models and just joined teams? We've already got a model. You got a good model, second place. You got a good model, third place. They're different because you guys all worked independently. And so join teams and figure out ensemble the model, right? Maybe, since your model's better, yours is 60% and this is 40%, or who knows, but you just try and figure it out. And then you resubmit. And then all of a sudden, you guys get to move in front of what was the first place team, because you're now in front. Okay. And there's some of that shuffling that happens at the end of every category competition, where teams merge and join together, and in almost all cases are ensembling, because that's the only reason they would do it. There's no reason I'm going to pick up another team unless I get something from them. What I get from them is a trained model. And I'm not going to replace my model unless they're ahead of me, but they wouldn't want me in if their model's ahead, and so by combining, you get a wisdom of the Kaggle competitors.
And there are no rules against collusion like that?
It is a standard form, and there are rules on when teams can join and so on, and it all happens at the end. Okay. So, it happens in real life. And your models, this could be a deep learning model. This might be a totally different model. Random forests has nothing to do with deep learning. It could be something different as well. So they don't need to be architecturally the same at all. And the reason this was okay is because you guys spent your 2 weeks on, sorry, you guys are no longer first place, I'm sorry. You guys spent 2 weeks on training your model, and you guys spent 2 weeks on training your model, but you were using your machines, and you were using your machines, and it did happen in parallel as well, because you had two different teams. So there's no cost kind of to merge your models together, or to ensemble your models, because they don't really get merged. It's just like, it's a completely separate model, it runs, it gets an output. You're just merging the outputs of the models. Okay. But you need to create different models, and they take time. Is there any way that we could do our training for 2 weeks on our thousands of machines, do no more training, and yet somehow ensemble? Do we have multiple models from our 2 weeks of training? Tell me about that, Ben.
If we had it within the...
That's why I didn't erase this. We say, how many models do we have if we did 100 epochs?
Depends how you say it, probably 100.
It's right here, 4 epoch save. Yeah, so it's 100. So we've got 100 mod now. The last 30 are crappy, right? Because we're overfit. The first 40 are, yeah, that's a good number. The first 40 are probably crappy because we're underfit. But the middle ones are okay. Some of them are better than others, but for us to ensemble, right? Some of them may be at different areas of our sort of our loss function and be good at certain things that our final one is not. So we have here kind of a cheap and easy way to get multiple models that we can use to ensemble. And maybe it's only going to give us 0.5% better accuracy. But if you're going from 97% to 97.5%, if you think about it, your error just went from 3% to 2.5%. That's much better. You had a question?
Do the models need to be a certain amount different from one another in order to effectively ensemble them? You know, 68, 69, and 78 of these are probably very close to each other.
Yeah, you would probably want them to be different. And the other thing is, sometimes your training regimen is such that you get fairly different ones. So if you start adjusting the learning rate, let's say you take the learning rate high and then decrease it to low, that'll give you a nice model. And then you could increase it to high again and then back low again. So that might take you to somewhere different. And then those two might be fairly different models. So.
Are there ever models that are purposely trained like that to get them sort of exploring different spaces and then ensemble?
I don't know the answer to that. So yeah, that's interesting. Your goal there might be not to just get sort of an absolute best generalizable loss, but to get a different area of the space loss that you could combine together. I don't know, it's a good question. All right, I want to start now on categorization. So this, we're leaving regularization, except we've got one thing on the back burner, which is noise to the wise. We'll get back to that. And I want to talk now about the categorization problem. So this is like the problem of happy faces. Except we're going to look at a much simpler problem because we're still using model, which is polynomial. And I know how to recognize happy faces and sad faces with a neural network, but doing that with a linear or even polynomial model is pretty hard. So our problem is going to be simpler. So our problem is going to be this. We're going to have one type of thing and another type of thing. So it's a binary classification problem. We're going to have, let's say, circles and stars. And I want to distinguish circles from stars. So the way we're going to do that, give me an idea, Raji. What could we use to know what's a star and what's a circle? In this case, what we have are locations. I'm sorry. So these are points on a Cartesian coordinate system, and the x's are the location, and the y is the label of whether it's a star or a circle. So if we really looked at the input, this might be 4, 8. So this is 4, 8 as a location. That's the x. And the y is 1, meaning it's a circle. These all have y's of 0. These all have y's of 1. And the x value of each of these, the information we have is just its location.
So you could start off with a line somewhere and
Uh-huh.
then keep moving the line until you're equidistant from.
Okay, so you want a line. Come up here and show me the line you want. Okay, so let's ignore for a second how to get there, although we know roughly the approach of how we're going to do it. But we need to make sure we know what f is, what a loss function is. We know how we'll optimize probably. Okay, so there's a line. We have a slope, we have an intercept. And you're saying above the line,
Like, pretty much you want to be the same distance away from the circles as you are from the stars.
that's fine. So you're saying if we had another line that was like this, that's just hugging the stars, it's not so good? Is that right? Okay, so let's look at your line. So how do we make a prediction? If I give you this location, what are you going to tell me the answer is? It's a star because it's below the line. And if we predict something up here, then we'll say it's a circle because it's above the line. Does that make sense? So this is a binary classification problem. Y is in what range? Sorry, Y is just a set, 0, 1s. We might have circles and stars, some data that's incoming. That looks like that. Rachel, what would you use in order to separate the circles from the stars? Would you use a linear function?
No.
What might you use?
Something more complex.
Like
Parabola.
Parabola probably. Looks like that it'll work here. So if you fit a parabola, maybe it'll go like that, and then you could say above the parabola, below the parabola. Right? Same idea. All right. So we know our data. Our data is x's that are coordinates and y's that are either 0 or 1. We need to come up with an f and a loss. Sally, any thoughts on an F?
For that one.
For here, well, let me back up a second. So before we used f of x equals a0 plus a1x, right? Because basically, we were predicting, given the first coordinate, what the second coordinate was going to be. Here, our input to the f is actually a pair, right? So it is, I'm going to call it x1 and x2, right? Might be 4 and 8. So we know our function is going to be somewhat different. We could, but we still have a0 and a1 that we're going to learn for this case because we think it's linear. We could have an f that outputs 1 if it's above the line and 0 if it's below the line. Right? So our f could be well, what we would do, we would say a0 plus a1x if a0 plus a1x is below, so let's see, x2. So this is on the line, correct? a0 plus a1x. So let's look at this specific example. Right, we're looking right here. a0 plus a1x is here. x2 is here. So x2 and a0 plus a1x. So a0 plus a1x is less than x2, so we want to return what? 1. Else, return 0. This could work. So we basically say our prediction is if it's above the line, 1, and if it's below the line, 0. When we get to our loss, though, we have a problem. Y, we know, is either 0 or 1. Y hat is either 0 or 1. Our loss does not have much to work with. Okay? In this case, our loss, because the choices are either we got it right or we got it wrong. But we don't have any good measure of how close we were. So we need to add some measure of closeness, I guess. What might we use? Anyone?
How
Jack.
far away
Not Jack, Jake.
how far away from the line it is?
How far away from the line it is? How does that sound? Would it seem reasonable to say, if we've got a circle out here, that we are, sorry, we don't have a circle out here. We have a point out here, and we have a point right here. If we were betting money, which one do you want to bet on is really a circle? The one farther away than the one that's right on the line. So I like that idea. Let's measure this distance here, right, this delta. Sorry, delta, capital delta. And that's what we can use as our loss. And then we will continue this on Monday, but just to point out a particular problem. If we look at this distance, we've got numbers that are not at all 0 or 1, right? And we're going to be comparing a 0 or a 1 to a small or big number. So we're going to have to do some sort of mapping from a distance into a number between 0 and 1. That's what we're going to do on Monday. Homework. I have homeworks here. They're due on Monday, and this is actually the weight decay. homework. I think I said it was next homework, but this is it. So the assignment, the program assignment is due tomorrow at 11 p.m. You're sharing it with me. I have office hours after this. I think that's it.